My name's Aaron Toponce. Here's my email. I work for XMission. I'm one of the system administrators. I'm on the sysadmin team. Crypto is kind of a hobby of mine. I have a degree in mathematics, and I specifically got that degree so I could learn more cryptography, with every intention going to grad school, and it never happened. Maybe someday, but not yet. So that's what we're gonna talk about. And I just lost. Something happened. What happened?
Do you work with Joaquin?
I do. He lives up in Oregon.
Oh, is he in Oregon now?
Uh-huh. That's where he's initially from. And his dad was sick, and so he went there to take care of his dad.
Gotcha.
And he's been there since. Let's try this again. Better. All right. I always license my presentations under the Creative Commons. If you go to aarontoponce.org/presents, you can find all my presentations there. So feel free to have at it. All right, so this is a kind of an introduction of what we're going to go over. I've got a lot of slides, so I don't mind answering questions, but if you could hold off on those till the end, that would be better. We could go out and talk. Or I guess there's no one after me, huh? So I can keep you here as long as I'd like. So this is kind of what we're going to go over. We're going to talk symmetric encryption, asymmetric encryption. We'll talk about the difference between encryption and decryption, what it takes, signatures and verification. We'll look at the Diffie-Hellman Key Exchange, the SSL Handshake. We'll look at the different SSL versions, SSL 1, 2, and 3 versus TLS 1, 1.1, and 1.2. We'll wrap up with some SSH and PGP concepts. So let's get rocking. First, symmetric encryption. Symmetric encryption requires the same key for both encrypting and decrypting the text, or the message, or the data, whatever the case may be. Historically, these have been substitution ciphers. You know, if we go like the Caesar cipher, for example, there are rotational ciphers, like I'm sure you've heard of ROT 13, right? ROT 26 is twice as secure. So a lot of classical hand-field ciphers. These are things like the Apbash cipher, the Vic cipher, which has an interesting story. If some of you are not familiar with the case of the hollow nickel, I'd recommend you look that up. That's a fun story about this newspaper kid who got some change from a customer delivering a newspaper, found one of the nickels to be lighter than the rest. He threw it on the ground and it split open, and inside was a piece of microfilm. The microfilm was just a matrix of digits, and it turned out to be an encrypted message for a Russian spy in the United States. And it kept the FBI and the CIA stumped until a Russian defector defected to a US embassy, and then they brought this to him and said, "You know anything about this?" And he said, "Yeah, and I can show you how to decrypt it." And that became known as the Vic cipher. That was kind of fun. Many of you probably heard about the one-time pad. The one-time pad is also a symmetric cipher, where your key is at least as long as the message itself. And the key is true random data, and then you can just do a simple addition, like a modulo-based addition, or you can use like the exclusive or something similar to take your plain text to the ciphertext and do the exact same thing to reverse it, which is why exclusive OR works so well. Other symmetric encryption ciphers, AES, triple des, blowfish. We'll look at a few of those in a second. But here's kind of how it is visually. You have a plain text, you use a key to get to the ciphertext. That same key can undo the ciphertext. One thing with symmetric encryption is the value of keeping that shared key secret. Obviously, if anybody else gets a copy of the key, they can decrypt what you're trying to hide, right? Which comes up with an interesting problem. If I can keep the key secret and deliver a message to my friend, then why don't I use that same method for just giving him rather than delivering him the key, why don't I just deliver him the message in that secure manner? That's why lots of people find the one-time pad to be impractical. Because if I have to give my person a copy of the pad, of the key, why don't I just use that to give him the message? So there's an interesting problem there.
Time shifting.
Time shifting, yeah. And I could generate more key material than I need for messages, and then we could agree on a way to use that key material until it's dried up. Here's some symmetric encryption algorithms. DES, the data encryption standard, has since been superseded by AES. The EFF wanted to show, so DES uses 56-bit modulo arithmetic. And EFF wanted to show how weak 56-bit security was, so they built a custom computer, custom hardware, that could brute force any encrypted DES message. And they were able to pull it off in 9 months to show how broken DES was. So it wasn't shortly after that we realized we need something new. And the advanced encryption standard, which there was a talk about that this morning, the first talk about how AES works explicitly, step by step, piece by piece. That was a good presentation. That's now become the standard. Triple DES is DES just 3 times. So it's basically 56-bit security appended to each other 3 times. Despite the weaknesses of DES, triple DES still remains secure today. Although it's not widely in use, there are no practical attacks to do a ciphertext-only recovery down to a plain text. RC4 is a stream cipher. Those previous and the rest of them are all block ciphers. RC4, or commonly referred to as ARC4, is a very common symmetric stream cipher. You'll see it in SSH. We've seen it in SSL. For those who have to maintain PCI compliance, you're now learning that you have to disable RC4 support in your SSL configs or you won't pass PCI compliance. So RC4 is beginning to show weaknesses. The security margin, which is how we gauge security in cryptography, is getting small with RC4. There's some other less known, less used encryption or symmetric ciphers. Cas5, Twofish and Blowfish, both designed by Bruce Schneier and some other cryptographers. IDEA was a patented block cipher algorithm. The patent has since expired, and so now it's public domain, basically. Serpent is another one. With symmetric encryption, specifically with block ciphers, we have to figure out a way how we're going to encrypt the data deterministically and then also reverse that deterministically. And so we have what are called block cipher modes. And we have a number of them, and I'm going to look over most of these. But here's a good, thorough list. Electronic code block, or ECB, cipher block chaining, cipher feedback, output feedback, counter, counter with CBC. These top 6 are what we would call non- or unauthenticated block cipher modes. These don't provide any sort of authentication or data integrity as part of the operation. So if I encrypted some piece of text using AES in CBC mode and sent that off to my recipient, there's no guarantee that the data he receives is sound or that it comes from me, right? So these are 2 problems that we have to solve. These final ones, the Carter-Wiegmann plus CTR mode, offset codeback, Galois counter mode, and EAX. EAX, interestingly, doesn't have, it's an acronym with no definition. I don't know how that works. So I tried to come up with one. I figured a Microsoft version would work, embrace and extend. I think it's fair that E stands for encryption and A stands for authentication, but I have yet to figure out what the X stands for. Exchange, maybe. So, but these 4 final are what we call authenticated block cipher modes. These not only provide me with the necessary encryption that I need deterministically, but it also authenticates the data along the way. So when I get the data on the other end as a recipient, I can verify that the data hasn't been changed, my ciphertext hasn't been changed, and if I've negotiated a secret key between the sender and myself, I can verify that he sent me this data and nobody else. So these are known as authenticated encryption and associated data block cipher modes. Past just listing what they are, I'm not going to go beyond that. That's past Crypto 1010. So, but we'll look at some of these ones. I'm going to shrink it a touch. So ECB. This is how ECB works visually. First off, we call them block cipher modes because we divide our message into blocks, which means, depending on the mode, we may need to make sure that the plain text is a multiple of my block size. Right? So if I decide that I want to use 16 bytes for my block size, I need to make sure my message is a multiple of 16 bytes, so everything divides evenly. So there are some padding things, like padding the end of your message, and there are different algorithms for how to do that padding to make sure that my message is a multiple of that block size. So here's ECB. We take our first block of plain text, we pass it through our block cipher encryption with the key. This could be AES, this could be the one-time pad, it could be two-fish, and out comes our ciphertext. And we do this for each block in the plain text until we're finished. And the decryption is just the reverse. We take our ciphertext, throw it through with the key, and out spits our plain text. As you can see, none of the modes depend on any of the others. There's no interdependencies. So both encryption and decryption are highly parallelizable. I've got 8 cores. I could divide the work into 8 and get that done 8 times faster than with a single core. Let's look at CBC. CBC requires a few extra things. First off, it has what's called an initialization vector. Some of you may have heard that and wondered what it is. An initialization vector is just a random number, commonly referred to as a nonce. Okay? It does need to be communicated with the ciphertext to the other side. So initialization vectors are usually public. In fact, they're always public. We're just going to prepend them or append them to the ciphertext and send it off. And then the recipient will know where to find the initialization vector so it can move through the decryption process. This operation right here is an exclusive OR. The initialization vector must be the same size as my block size, so I can go through bit by bit and do an exclusive OR on the data. That result is then fed into my block cipher encryption with my key and out spits my ciphertext. Besides the initialization vector in this XOR operation, we also feed the ciphertext in as the next initialization vector for the second block of plain text. Right? And we continue this chaining all the way through until we get to the end. I'm going to show you why in a second, but I want to get through some of these modes. Decryption is just the reverse. I take my ciphertext, go through the decryption, I get an output. I exclusive OR that with the initialization vector that was shared as part of the ciphertext, and I get my plain text. The ciphertext is then carried off in a continuous manner. Unfortunately, encryption cannot be parallelized, but decryption can with CBC. Cipher feedback. There's two that are really close. There's cipher feedback and output feedback. And I want you to see if you can tell the difference between the two images. So here's cipher feedback. There's output feedback. Cipher feedback, output. With cipher feedback, my initialization vector and output feedback is fed through, and this is what gets encrypted. Then my plain text is exclusive OR'd with whatever comes out of this operation, and that result is sent as the next initialization vector. Right? With output feedback, however, I take the result of my encrypted initialization vector and feed that into the next block. Before doing the exclusive OR with the plain text. So we'll go back and see that again. Cipher feedback, I'm working on the ciphertext, which is why it's called cipher feedback. And output feedback, I'm relying on the output of the block cipher encryption. Interestingly enough, cipher feedback, only decryption can be parallelized. But with output feedback, neither encryption nor decryption can be parallelized. Also, another interesting observation. Notice with my decryption that really I can do the encryption process twice. Notice that? I don't have to have a separate decryption function for this. And it should be clear why. Next is counter mode, or CTR mode. Counter mode is very similar to ECB, except for one difference. Rather than taking my plain text through and getting my ciphertext, I have a counter that I'm going to increment one by one across. That's what gets encrypted, and then I just exclusive OR the plain text with it. But other than that, you'll notice there's no interdependencies between the blocks. So counter mode can be both, can be parallelized both on the encryption and the decryption process. Counter mode is usually preferred because it's cheap operationally and it's fast. So as a, I don't want to say cryptographer because I'm not a cryptographer. As a software designer, software developer, if I'm designing an application that's going to be using AES, I'm going to want to use CTR mode to take advantage of this performance benefit. Now, there's a problem with ECB mode. If you remember ECB mode, I just took my plain text, fed it through the block cipher encryption algorithm, AES or twofish or whatever, and out came my ciphertext. Here are some commands. You can do this on your own computer. But I grabbed a bitmap, openwest.bmp, and I encrypted it with AES 128 in ECB mode and in CBC mode. Okay? And I got out two different bitmaps. Technically, this is just random garbage data junk. But what I did take is the first 54 bytes off of my bitmap, and I applied them. So here's my input file. Read the first 54 bytes off of this and apply it to that. Now a bitmap image utility will be able to process this data and take a look at it. Then I converted it to PNG files because they're easier to show in web pages. And here's the result. There's the original Openwest logo. Here it is encrypted with ECB mode. And here it is really encrypted with, this is with CBC, but any other mode will produce similar results. The point is, ECB maintains plain text structure, right? For if two blocks are identical, they'll get encrypted to identical ciphertext blocks. Everything else, that's not the case, but with ECB it is. So on images, it comes out pretty clearly that you can see it's maintaining the image data structure, where in the case with CBC, it's not. Does that make sense? All right. So enough with symmetric encryption. Let's look at asymmetric encryption. Asymmetric encryption is commonly referred to as public key cryptography. Symmetric encryption, we have a shared private key. No one else should get a copy of this key. But with public key cryptography, or asymmetric encryption, both the sender and the recipient both have to generate a public and private key pair. The public key is then shared with the sender or other recipients, multiple people, but they hold on to the private key themselves. So the public keys are distributed. There are even public key servers where you can put these public keys up for people to download. People put them on their web page, their business cards, right? Some algorithms include RSA, ECC, and the Diffie-Hellman Key Exchange. We'll look at some more of that in a sec. To get an idea of how asymmetric cryptography works, the public key is responsible for doing the encryption, where the private key is responsible for doing the decryption. That makes sense, right? If I wanted, Kevin, I'm going to pick on you if that's right. If I wanted to communicate securely with Kevin using public key cryptography, he would need to generate a public and private key pair, as would I. I would then send Kevin a copy of my public key. He would send me a copy of his. In order for me to send encrypted data to Kevin, I'm going to encrypt the data using his public key. Then I go ahead and ship that off. I can put that on a website to download, put it in an email, whatever the case may be. No one should be able to grab that and decrypt it unless they have Kevin's private key. Hopefully Kevin's the only one that has it, so Kevin should be the only one that can decrypt it. And if Kevin's private key gets leaked, that's his problem, not mine, right? And the same, the reverse is true. Signatures and verification work similarly, which I don't have here. talk about, I guess, that in a sec. So here's, I guess, a visual explanation. We convert plain text to ciphertext using a public key. We convert ciphertext to plain text using the private key. Here's some common asymmetric encryption algorithms. Gamal, RSA, elliptic curve cryptography is a public key crypto system, and the Diffie-Hellman Key Exchange. Different protocols that use asymmetric encryption. S-MIME. S-MIME is, for those of you who have Outlook as your email program, you can set up Outlook to sign your emails with an SSL certificate. Lots of government contractors and government agencies will do this, and some larger corporations will do it. S-MIME is the ability to attach your public SSL key to your email as well as the signature. So when I write an email, I compose an email and I sign it, what I'm stating by signing that email is saying that this email was written by Aaron Toponce and nobody else, right? And if you can successfully verify that the signature is valid on that email, then no one tampered with it. So you can rest assured that I'm the one that sent the email, I'm the one that gave you that data, nobody else.
But if you're signing it with public key is public.
You don't sign with the public key, you sign with a private key. Yep. I don't even know if I should be getting to that. But yes, you sign with a private key because I'm the only one that should have access to that, right? I'm the one making the statement called non-repudiation. Basically, you can't say I am anybody else than who I claim to be, and that signature proves it, right? Then it's verified with the public key. Yep. GPG or PGP both use asymmetric algorithms. SSH. You thought about that. When you SSH to a server, for your first time, you're presented with what? A fingerprint, right? You're presented with the key. And then you're asked, do you want to accept this, yes or no? Now, you don't have to show by raise of hands, but how many just blindly copy yes and then type in your password and move right along, right? You should be verifying that fingerprint on that first connection. I mean, who's to say that there isn't a man in the middle that's redirected you to another SSH server and is only hoping to get your password, right? So verify the fingerprint before you type yes. But what you're getting is the server's public key, right? That's what you're getting a copy of. It's saying, here's the server's public key. Do you want to accept it? Sure, I'll accept it, authenticate, and I'm in. From here on out, everything is encrypted with that public key and decrypted with the server's private key. So SSH uses public key crypto. And if you do key authentication instead of password authentication with the SSH keygen command, same thing. You generate a public and private key. The private key you keep on your workstation, the public key you send out to the server. Then when you SSH over, it'll use the public and private key together as a form of authentication to let you in versus your password. So SSH uses public key crypto. Bitcoin is another public key cryptography system. OTR, off-the-record messaging. Tomorrow I'm going to talk about end-to-end encryption, and we'll look at OTR a little bit more in depth, but OTR uses public keys. So, signatures and verification. Signing data non-repudiates that data. That basically says that no one else can take claim to this data other than the person who signed it, right? There are times when this is appropriate. There are times when it's not, obviously. If you're a journalist and you decide to do a whistleblowing, you want to remain anonymous, you probably don't want to sign your email with your GPG key or SSL key. But if you're lawyers working with clients, maybe you do. Maybe you do want to sign your email so a client or another lawyer can't use a forged or modified copy of that email against you. So think of it like a physical signature, but stronger. And again, signing requires a private key because you're the one doing the signing. I should be the only one that has access to that private key. Verification requires the public key. And here's that visually. Take a message, sign it with the private, and we verify it with the public. All right. I guess we are moving at a good pace. Are there any questions up to this point or comments?
One thing that escaped me as I sat through a first class on this was that some algorithms allow the reversibility of the signing with either private or public. Not all of them do. There's some. So you mentioned, the one guy had a question about, well, which key do you sign it with? The public or the private?
You should always be signing with the private, because you're the only one that has access to it. So there shouldn't be any signatures done with the public key. Now, there are a different type of signatures that we'll talk about in a second that don't require public key crypto, but use what's called digital cryptographic hashing algorithms, like SHA-1, for example.
I guess I misspoke, not signing, just the fact that the algorithm works.
Yeah, right. The public and private key pairing, they both have two responsibilities, and intuitively it kind of switches between encryption and signatures.
Yeah, so anyway.
Yep. Is there a comment? Yeah.
So if you're using SSH to connect to another machine, you have a generated public and private key pair on your machine.
Okay.
Doing password authentication.
Uh-huh.
Does it basically then just create a key for you based off of your password? Or do you know how that works?
No. So when you SSH is actually a hybrid encryption. You get a copy of the public key, so when you want to type data to the remote shell, it's going to get encrypted on your box with that public key first, and then sent through the wire encrypted, and the server's private key can decrypt it. Actually, if you look a little bit closer, it's a bit more rigorous than that. The public key part will actually generate a symmetric key, like an AES key, encrypt that key with the public, and send that off. Then from here on out, that AES key is what's used for the encryption and the decryption. The public key that the server sends you is only really used to generate that symmetric key. The problem is public key and private key encryption is expensive. It's just not as performant as symmetric encryption. So we use the public key, and GPG does the same thing. We use the public aspect to generate a temporary session, one-time symmetric key, and we use that for the duration of the session. Does that make sense?
What is, on my end, when I receive data back from the server that I've SSH'd into, what am I using to decrypt that?
So here, I'll give it to you visually.
Your machine creates the symmetric key and sends it encrypted to the server.
Oh, okay.
So
Right.
Then after that, you just use the symmetric key.
Correct. Yep. You get the public from the server, and they have the private. Your public key generates a one-time AES key that you encrypt with his public key, and that gets sent over encrypted to the box. And then a backwards S. I've never done that before. That was interesting. And then that AES is what's used to encrypt your session from there on out.
Okay, that would be different than every time I log in, my password is the same.
Right. Yeah, your password is actually on the authentication side of things, whether it's LDAP or local authentication or whatever, right?
Yeah.
That's handled locally. The SSH server is just kind of handing that off. Yeah.
Which is similar to what SSL is, right?
Correct. Yeah. Yep. You'll find that actually most public private key crypto systems don't spend the entire session using the public private key doing the encryption the entire time. Instead, we'll generate these session keys and use the symmetric encryption to get that performance. So, your questions, yeah?
Now you mentioned like on signing, this is like in an email situation or something like that, that attached to that email is your private key.
No, you're public.
Okay.
You're public,
okay,
yeah.
public key.
No, yeah.
Okay, I thought I had heard private, and I'm like, well, then everybody have your private key.
Yeah, no. If I did, I apologize. The public key with SMIME is attached. So that way, recipients of the email don't have to go looking for the key. They just use the public key that's in the email. It's in the email headers.
Okay,
But, yeah.
gotcha.
Yep.
Does this on the browser work the same way?
Yes. Yep. And we'll look at the SSL Handshake here in a sec, actually. Yeah. Okay. Good questions. So let's look at some digital signature algorithms then. There are a number of different signature algorithms. There's RSA-based schemes. RSA is a public crypto system, but it also handles signing, such as RSA Probabilistic Signature Scheme, or RSA PSS. Some others from the Digital Signature Standard, which is a NIST and FIPS standard. Take that for what it's worth. I'm not saying to trust NIST, but it is an industry standard. DSA is the Digital Signature Algorithm. And ECDSA is the elliptic curve equivalent, elliptic curve digital signature algorithm. It's a tongue tie. What's interesting with RSA and with DSA is they require large primes, right? In fact, some of you who might be familiar with DSA know about DSA's secret key or private key. If you're familiar with the Sony PlayStation hack that happened a while back, people figured out the private key to the Sony PlayStation. Was it the firmware, I believe, the PS3 firmware? It's because they did not use a strong pseudo-random number generator to generate that prime, that secret key. And so after a number of signatures, mathematically, we were able to derive the key, and as a result, pretend that we're Sony and sign anything with Sony's key, even though we never actually got a copy of it. There are some approaches to that. We won't go into them. But ECDSA, elliptic curve, doesn't rely on primes. Instead, it relies on elliptic curve fields, which is a completely different field of mathematics versus factoring prime numbers out of large composites.
Is the DSA, is that the DSA-based schemes, are those the ones that are kind of that could possibly be in jeopardy because of Google's quantum computers?
Yes, so quantum computing is a serious threat to prime-based factoring, basically, yes, because of an algorithm called Shor's algorithm. Currently, it's up to you whether or not you want to believe the D-Wave computer is a legitimate quantum computer, but there are no practical quantum computers that are really threatening us right now. But Shor's algorithm, should quantum computing become a thing, seriously puts RSA and DSA into big time jeopardy, because now we can become more efficient at factoring out primes out of large numbers.
You're saying that won't affect the discrete logarithm problem for ECC?
Correct, it doesn't, nope. And it doesn't affect AES, it doesn't affect any of the secure hashing algorithms. It only affects algorithms that require factoring out primes out of large composites. Yep, which right now is really just RSA and DSA. So.
But is there an issue with DSA? Because in order to comply with the certain standards, a 1024 limit, in a 1024 you might want something bigger.
Yeah, I don't know if the security margin, even with the 1024-bit DSA key, is large enough that it's not a problem. People mostly shy away from DSA because of the secret K value. If your pseudo-random number generator is not cryptographically strong, then with verifying enough signatures, we could determine that K and recreate the private key and then masquerade as you. That's the weakness with DSA. But if you have a secure, strong, cryptographically secure, true random number generator, DSA is not a problem. So that's really the only hiccup with DSA, and that's why people are shying away from it. So when we talk about digital signatures, it's hard not to talk about cryptographic hashing algorithms. Technically speaking, these are not public key algorithms. In fact, these are what you would call digest algorithms. They're compression algorithms. They take an arbitrary size of data and compress it down to a deterministic size of data. And this becomes a fingerprint of sorts that represents the data that you just compressed. With that said, these are used in a lot of time in signatures. For example, with S-MIME or PGP-MIME, even though you're signing the data with your private key, what you actually are doing is sending your email through something like SHA-2. You get a digest, and then you encrypt that digest. Lost the data. and you send that encrypted digest off with email. Uh-oh, there we go. I went a little too far back. So really, these cryptographic hashing algorithms are used all the time in digital-based signatures. So it's worth working on, or commenting on. SHA-3 Keccak. This was recently just announced as a standard for NIST. Keccak was the winner of a, say, 5 or 7 year hashing competition to replace SHA-2, and it would be dubbed SHA-3. It's been sent off to FIPS. FIPS is requesting comments. They've received their comments. So any day now it should be a finalized, formal, documented standard. But we haven't gotten that stamp of approval yet. But I don't think anything's going to change. So if you see some SHA-3 implementations of Keccak on GitHub or something, check the reference. If the reference matches, it's probably good. Then some other less known, RipeMD, Whirlpool, Tiger. What's interesting with RipeMD, so we're all familiar with SHA-1, right? It's the security margin is weakening big time. It's a 160-bit hashing algorithm. RipeMD is another hashing algorithm, came out just a bit before SHA-1 actually, and there's a 160-bit variant called RipeMD 160. There are no known weaknesses against RipeMD. Now granted, it hasn't gotten the same attention that SHA-1 has, but RipeMD has been around since I want to say 96. So it's almost 20 years old, and it still stands secure where SHA-1 is falling apart. So if you're looking for a lighter, faster algorithm, I'd recommend RipeMD. All right, Diffie-Hellman Key Exchange. This is the ability to exchange private keys exchange private keys using a public key crypto system, like I explained here with SSH. How do I get this AES key from my laptop to the SSH server? The Diffie-Hellman Key Exchange is one way. So first off, we need to know that it's vulnerable to man-in-the-middle attack. There's nothing that prevents me saying, well, this is really the actual server that I want to SSH to, but someone is sitting in the middle. I exchange, we'll say, AES1 with him, and he exchanges AES2 with the other box, right? And then even though I maintain this connection, really I'm encrypting everything here. He decrypts it, re-encrypts it for the server, and sends it on, right? Diffie-Hellman is vulnerable to a man-in-the-middle attack. However, this is how it works. With Diffie-Hellman, both sides generate a secret, and then A will encrypt a message with his secret, send his result to B. B will encrypt that ciphertext with his secret, send it back to A, and then A can decrypt the ciphertext, and both will have the key. If we want to look at this visually with paint, here's a good way how it looks. Here's Alice and Bob. They both have a common paint color, yellow. They both generate their own personal keys. One's brown, one's blue. They encrypt it or mix the paints and get the color. They then swap the mixed paint. Now I can apply my key to this paint to come to this lovely brown. And I can do this, Bob can do the same, and now we both have a common secret. This can now be used as my shared key for the encryption and the decryption algorithm. If I can make that a bit bigger. So that's Diffie-Hellman. Again, though, there's nothing to prevent someone like Eve sitting out here with her own, I guess I should put Eve in the middle, gets a copy of Alice's tan and Bob's blue, and then generates her own secret to apply those and then do two Diffie-Hellmans between both of those parties so she can do the encryption decryption between Alice and Bob. Is there a question back here?
My question is just kind of along that line. But it's only susceptible to the man in the middle if you're not talking to the computer you expect you are, correct?
Yeah.
But it is secure in that if there is a man in the middle just listening, they won't be able to get the key, right?
What do you mean?
So if the connection is just being watched,
Yeah,
They can't derive what the key
the man in the middle is an active attack, not a passive one. Yep. Yeah.
Is it possible to do key exchanges that are the man in the middle attack is not?
Yes, we're getting there. Yep. It is possible to do a Diffie-Hellman and close that man in the middle vulnerability.
Why do both of them have yellow color as common paint?
This comes back to the private and public key part,
Okay.
right? So they both have a private and public key piece. They've both sent off each other's copies, and so they both have the same state. Yep. Other than the private key, which is different. Yeah. Yep. Any other questions? All right. So let's look at the SSL handshake. Someone asked about that. So the SSL handshake is actually very similar to Diffie-Hellman. Client issues a hello. The server sends off the public certificate, right? This could be your browser, for example, or your email client. The client authenticates the certificate. This is actually a mouthful. This is where SSL, in my opinion, has some problems. But we have to have a certificate authority, right? And then there's probably a chain that goes back to a root authority with signatures all along the way to verify that the certificate I received is a legitimate, valid certificate and not one that's been forged. Part of that is checking like the common name, right? I'm sure you've seen that where you go to foo.example.com, but the certificate is only valid for www.example.com. And so you get a certificate error, right? That's because it's not matching the common name, so we can't even verify the certificate's authenticity. For all we know, someone came in the middle and gave me a bad cert. So again, there's a lot of work here. But once the client has successfully verified that this public key is good, we go ahead and generate a secret, encrypt that secret with the cert, send the encrypted secret off to the server. The server decrypts it with their private key on their end. And from there on out, the SSL or TLS connection is encrypted with that shared private secret.
So in this instance, if we were to take the example of a website, it's really dependent upon the integrity of the browser, since it's doing the handshake with the server.
Yeah, so the browser is going to have what's called a certificate store. Your operating system will probably have a similar certificate store. And these are going to store common, trusted, certificate authority public certs, as well as maybe a number of chained, some root authorities, and so forth. So your browser, when it gets the certificate from foo.example.com, it'll say, oh, this was signed with DigiCert. Do I have DigiCert's public key in my certificate store? If I do, I can verify if the signature is valid on that cert. But then DigiCert is signed by, and they are signed by, so I have to kind of go back the chain and make sure all these signatures are valid before I can continue on to the next step.
Thank you.
Yeah, but, and it's a pain in the... One thing I hate about PCI compliance is dealing with SSL certificates. It really drives me nuts. So, any other questions on that? All right, so let's look at SSL versions then. This is going to be kind of fun. Many of you probably are not familiar with the differences between SSL and TLS and all the versions. SSL 1.0, developed by Netscape in 1993, was never actually released. And the reason it wasn't released is this last thing right here. Vince Cert was sitting in a presentation about Netscape's going over SSL. He's on his computer and he breaks what they're just presenting in 10 minutes. There were some serious problems with SSL 1.0. So it never actually got released. Some interesting things about it, though. There was no data integrity, no signature algorithms, so I couldn't verify that the data has not been manipulated. Later, in SSL 1.1, we added the cyclic redundancy check, or CRC, as a way to verify data integrity. RC4 was used for the encryption. It was vulnerable to replay attacks. There were no RFC documents. Really not much to say about it other than it was not released and kept internal to Netscape only. However, a year later, they did come out with SSL 2.0. This was the first public release, and it used RSA for the crypto, and then MD5 for the data integrity. Okay? And these had large safety margins at the time. We now know that MD5 is completely broken, and we know RC4 security margin is slimming, so we're recommending people get off it. But at the time, it was safe. What's interesting with it is during this time, there were United States cryptography export laws, which stated that if you developed cryptography in the United States, you were limited to a certain set of restrictions before you could copy that software outside of the country. If you did not follow those restrictions, you were charged with munitions, right? We'll talk about Phil Zimmerman here in a second, but he was a target of that. So we have this export setting in SSL 2.0, where in order to comply with that law, RC2 and RC4, RC2 is another supported encryption algorithm, were limited to 40 bits of security. This was so the FBI or the CIA could intentionally decrypt your data without much work, right? We thought we had problems now. It was deliberate then. Okay. But if you kept it internally, you could use 64-bit DES, 128-bit IDEA, 192-bit triple DES. The only mode, the block cipher encryption mode, was CBC, supported at the time. Turns out this is actually not a great choice. It's better than ECB, but we'll look at some problems with it here in a sec. But this was SSL 2.0. Yeah?
You know if at the time that the U.S. government was probably the only entity capable of breaking that?
I don't know. 1993, I wasn't old enough to care. I honestly don't know what other countries. It wouldn't surprise me if some of the United States allies like the UK or, Great Britain had the possibility. I don't know. I don't know what the technological power was at that time.
And the note to make, and this came out semi-recently, is that SSL2 still supports that setting, and a lot of servers will respect the downgrade to 40-bit.
Correct. This was, a recent attack that, thanks to POODLE. POODLE was part of that, part of CBC, part of what's called an oracle, which we'll talk about in a second, but also would intentionally downgrade you to 40 bits, export mode. So some SSL 2.0 weaknesses. Vulnerable to man-in-the-middle attacks because there's no authentication on key exchange. Vulnerable to a cipher suite attack, which is basically the client or software forcing the server to negotiate a weak cipher. Vulnerable to a truncation attack. Uses weak MAC construction, a message authentication code. This is what authenticates your data integrity. The client handshake could not be interrupted, so you'd have to restart. There was also no certificate chaining. Oh, a little bit big. I don't know if I can make that smaller. SSL 3.0 came out a couple years later due to the flaws in 2.0. I notice I'm running out of time. It was a complete redesign. We finally have an RFC attached to it. Typo. MD5 and SHA-1 are now the cryptographic hashing algorithms supported in SSL 3. We also got a couple more algorithms, DES, triple DES. There was RC2 and RC4. We still maintain that 40-bit export, which, by the way, these export laws were eliminated with President Clinton. So when he was president. We maintain backwards compatibility with 2.0. We finally get certificate chaining. We now have RSA, Diffie-Hellman, and Forteza key exchanges. I didn't talk about those. I'll let you look those up. We allow for both compression and decompression, and we allow the client and the server to negotiate a cipher specification. This became known as the Cipher suite, but we still only stuck with CBC mode. Some weaknesses. RC4 turns out to have some strong biases. That's one of the problems with it, why its security margin is thinning. CBC was not authenticated, so as a result, we could do what's called a padded oracle attack. The padded oracle attack is guessing Basically determining whether or not I'm going to get an oracle error or I'm going to get a protocol error. If I get an oracle error, I can use this to my advantage to decrypt the data without a key. And because of CBC and another problem with how SSL is designed, we've had a lot of these oracle attacks. We've had Lucky 13 in February 2013, which is an oracle attack. We've recently had POODLE last year, which is another oracle attack. And there are bound to be more because of the way it's designed. The Beast attack, Lucky 13, POODLE. So we move to TSL 1.0. TSL 1.0 was largely the same as SSL 3.0, but they're not identical. There are some differences. I've seen some people confuse these and say that they're the same. We have the same cipher suite, but the big difference is we add ephemeral Diffie-Hellman. What ephemeral means is that we can authenticate the data, right? If I say with the recipient, we agree on a private key and we sign the data, I can verify that data integrity. So as a result, we have what's called authenticated CBC. That was the big difference between SSL 3 and TLS 1. Turns out there's some weaknesses. We've got a couple bad algorithms. MD5 is completely broken. SHA-1 is weakening. Other than that, though, we have DES, RC4, and RC2, some bad stream ciphers. We still support the 40-bit export mode. But overall, though, TLS 1.0 is not considered insecure. Despite some of these weaknesses, it still only sits in the theoretical realm for possible attacks. TLS 1.1 released 2006, several years later, defined in a new RFC, and we dropped RC2. We also added the SHA-256 algorithm, which is what we've been moving to now with PCI compliance. We also added AES. We added ephemeral Diffie-Hellman with DSA or RSA, so we have our authenticated CBC. We get explicit initialization vectors versus implicit. We change on how we handle padding errors, and now we support IANA registration of parameters in certificates. Going through these a bit quick, I realize we're out of time. Some weaknesses. No real flaw. We do support MD5 and SHA-1 still. Even though MD5 does have collision attacks, it is still strong against pre-image attacks. The difference is, with MD5, I can generate 2 files that I know will produce the same digest. The problem is I don't know what that digest will be until I'm done. A pre-image attack says I have the digest. Now I would like to produce a file that get a file that produces that digest. MD5 is not vulnerable to pre-image. And what an attack on TLS or SSL require with the secure hashing algorithms is a pre-image attack. So even though MD5 is still supported and SHA-1, this isn't a concern. Okay? Now with that said, in order to break a pre-image attack, you have to break the collision attack. MD5 is broken in collisions. It's done. The nail has been sealed in the coffin. So that means it's only a matter of time before we do break the pre-image. Right? So that's why we've been recommending people get off MD5, and as a result, SHA-1. But other than that, no real solid weaknesses. TLS 1.1 is secure. TLS 1.2 released a couple years later, new RFC. We drop RC4, IDEA, and DES cipher support. So we're only stuck with AES, triple DES. I think those are the only 2. We drop 40-bit export mode. No longer require that. We replace the pseudo-random function MD5 SHA-1 with SHA-256. We mandate support for AES. The encryption now must be done with AES. You don't get to choose. But you can agree on different hashes and ciphers with different hashes in the cipher suite. And now, here's what's fun. We added Galois counter mode and counter with CCM mode, which is authenticated and associated data, like I mentioned. Now we have our authenticated block cipher support. Also, we'll never negotiate SSL 2.0. SSL 1.3 is currently in draft status. There is an RFC for it. We dropped compression support. Turns out there's some weaknesses when using compression and encryption. These are a couple of the attacks. There's a crime attack and a breach attack. We drop renegotiation support. We drop non-authenticated encryption ciphers. So everything has to be authenticated from here on out. We drop anonymous Diffie-Hellman Key Exchange. That means that there's no authentication when I'm sharing keys. So we have to force authentication. We drop RSA because it's anonymous. And then we drop all backwards compatibility for SSL or RC4. So TLS 1.3, it's TLS or nothing. All right, coming to the end. OpenSSH initially was created by a Finnish developer, Tatu Jalonen. OpenBSD decided to create a fork of it that they called OpenSSH. Technically, it was forked from OSSH, which itself was a fork of SSH 1.2.12. It first appeared in OpenBSD in 2.6, which was 1997 or 8, and then a portable release for Linux and Windows and everything else in 99. What's interesting is Tatu Jalonen threatened the OpenBSD developers for trademark violation of the term SSH in 2001. What he didn't think through was he had already created an RFC before he made it a trademark. He had already created a protocol design specification that was open. So he made all these open things available to the internet and then decided later that he wanted to enforce a trademark on it. And it didn't go anywhere. So, but as you can see, it's defined in several RFCs. Some concepts, different algorithms supported. Cha-Cha 20 is a new one, which comes from Daniel J. Bernstein, DJB. It's a block cipher algorithm. We have a number of different signature algorithms for our message authentication codes. We have a number of different key exchanges. Curve 25519 being the new, what's called a safe curve. Daniel Bernstein defines rigorously what that means. But Curve 25519 and Cha-Cha 20 are kind of like the new hotness in SSH right now. CBC and ARC4 are supported, but they're disabled by default. And after OpenSSL with the Heartbleed, for those of you who remember that, Heartbleed was because the OpenSSL developers put in a heartbeat extension to keep an SSL connection alive if no data was actually being transmitted. And that opened us up to Heartbleed. LibreSSL decided to drop heartbeat support. They dropped a ton of other stuff, completely forked OpenSSL. And now you can build SSH against LibreSSL. You don't have to require OpenSSL as a dependency. It supports Kerberos tickets, password and key-based authentication, and it provides not only SSH, which is a secure remote shell, but it supports secure FTP and secure copy. And as many of you know, it also supports tunneling. You can tunnel through firewalls with SSH, which is kind of fun. Finally, PGP. PGP was developed by Phil Zimmerman in 1991. To make it available to the public at large, he printed the source code in a book and then made that book available for print across countries, deliberately ignoring the export laws. But there was a loop back with published documents that he was hoping for. The FBI did come against him. They filed a case. It lasted for years, but it never went anywhere, and they eventually dropped it. So he wasn't found guilty of munition support. Eventually, OpenPGP came along. It was unencumbered PGP. No patented algorithms in OpenPGP, defined in a number of RFCs. What's interesting, what should be specified is OpenPGP is a specification. It's not an implementation. Okay? OpenPGP is an RFC. Think of it that way. It's a document. It is not software. With that said, there is an implementation. There are a few. The most common being GPG, or the GNU Privacy Guard. This is an implementation of OpenPGP, command line only. This is a public key and symmetric hybrid crypto system, like we explained with the private AES keys. Lots of third-party GUI utilities. There's Enigmail for Thunderbird. There's KGPG, GPA. There's even GPG utilities for Windows and Mac. These are all the algorithms it supports for public key. It's symmetric ciphers, it's hashes, and then whether or not it supports compression. And that is my conclusion. Sorry I kept you over. Are there any comments, questions, or rude remarks? Yep. All right, thanks, guys.